there. I'm right there. I like this. Yeah. She's that on your head. Mine shit. I like this. We always like at this angle. Back there. I can see it. I moved it right there. I hate that desk.
Oh, I still got really good. She's sitting in front of me. I'm okay with that. I can live with that.
You're right there.
Sorry. No, I don't like to sit here. I'm good with that here.
I figured that.
Did you guys even move?
No, they didn't. No.
What's the probability of having or going into cardiac arrest after taking
What's the probability of you shutting up?
not very good, I'll tell you that much.
It'll be good after I'm done.
I'm pushing this, buddy. I want no fun. You got it.
Why would you want to
Because it was ridiculous. I had a student last block sitting right there where Zoe's sitting, with this phone right in front of him, and I was sitting back there, right behind him. And he thinks I don't know what he's doing, sitting here doing this. Number one, we talked about discrete in the previous chapter. Anybody remember what's discrete mean? There we're going to review a little bit.
finite?
So discrete is finite. That's where we're finding the probability of stuff like you get a 1, you get a 2, you get a 3, you get a 4, you get a 5. That didn't include what? Decimals or fractions or any of the other stuff. We said that those are when you're dealing with continuous. So if we're on a number line, discrete, we're just looking at getting a 1, getting a 2, getting a 3. What we're going to cover now is continuous. So not only could you get a 1, but you could get any of this stuff through there. And that makes it quite a bit harder. Because how many numbers are there between 1 and 3? A lot. A whole bunch. And so we can't do what we did in the past where we just took this one and found the probability here and added it to this probability, because there's too many numbers. We'd be adding up for the rest of our lives. All right? So there's ways to do it. And what we're going to talk about is a normal distribution, which we've already talked about earlier this year, sort of. What's that called again? Bell curve. And it's actually a normal distribution is what it is. And then a standard normal distribution. We talked about this a little bit. Standard normal distribution is when we change everything to some standard form. The standard form that we're going to use most of the time is those z-scores. So we're going to change stuff into that. So we have a normal distribution where you have your raw scores on here, like the mean might be 752 or something. I'm just making up numbers. Then if we change it to, that would be a normal distribution. If we change it to a standard normal distribution, does anybody remember what the mean is when we're looking at it? If we change it to those z-scores? Zero. All right, so we're going to look at both of those and find the probabilities of all of them. We're also going to find, go backwards of that and find the values. Say, all right, if Leah wants to be in the top 10% of the class, where does she need to fall? Sampling distributions, central limit there, and we'll talk about that towards the end of the chapter. Normal approximation of a binomial distribution. All this is saying, when it says approximation, what's that telling you that you're doing? We're approximating. We're sort of rounding it off somehow. So it's not actually what this is, and this is probably what's most important in our real world, Because if I was to put all your grades, all your test grades on a graph, is it really going to fit this normal curve, this bell curve? Probably not. But is it going to be close? Probably it should be. And so what this is doing is approximating that to the normal curve. So even though it doesn't fit it completely, it's close. Properties, let me get this out of your way a little bit here. Properties of a normal distribution. Remember discrete, that was last chapter, that's what we just talked about. Continuous. Continuous random variable has an infinite number of possible outcomes that can be represented by an interval on the number line. So in this case, I'm going from 0 to 24. Again, please don't write, when I put these PowerPoints up here, don't write stuff word for word, because it takes too long, and it's, the main thing that Phoenix needs to know on this is continuous. We're including all of what? Everybody knows? You guys told me a few months ago. Mr. Simpson had trouble getting up this morning, didn't he? It contains all the decimals, fractions, everything else.
Simpson has trouble staying up.
But Sean has trouble walking, so that's,
He just sleeps all the time, is that what it is?
yeah, right.
It's not at
How
night,
it is.
you know.
I didn't wake up before dinner all break, but I stayed up till like 7 a.m.
I haven't seen you since last week.
It's true. Missed my birthday.
Your birthday is about Christmas?
Yeah, not really.
You missed it back in like February. No.
Did you have a good New Year's Eve?
I'll give you a hint. It was this month.
Are you a New Year's baby?
Birthday being at Christmas. Would you get double the presents?
No.
No, you get just half the
You get
presents.
one or the other.
That's
It's
what's so good about
combined.
having a December 9th birthday. You get presents and then you get away like 2 weeks and then more presents.
I think so.
I never got presents for my birthday. I never got like birthday presents. Yeah, I just got like 20 bucks and they were like, happy birthday.
Usually I do, but
I don't know what
I saw your dad post.
Yeah.
Your dad took a picture eating.
this doesn't really say anything. It's just that we're going to find the probabilities of that. Just to give you a little idea here. What's this called again? Some of you missed this on the exam. That sort of worries me.
Histogram?
It's called a histogram. What's it not called?
Bar
A bar graph. What would be different about a bar graph and a histogram?
Space in between.
Bar graphs have spaces between the bars.
Histogram, everything's touching.
Histogram, they gotta be touching. Now, you gotta be careful, because I think the one that's on my stuff actually has another thing that's out here like this.
But that just means there's a zero.
That means there's just nothing there for that bar, all right? So it's still a histogram, but, so don't call that a bar graph. Notice though, if we took this histogram and I drew this, it sort of fits that bell curve. Even though it's not exact, it sort of fits it. And that's what we're doing now. And we look at this, and this says 5, that's the midpoint. So we're starting down here at 0, 5, going up to here. What this is going to do is allow us to say, not only are we talking about the stuff from 0 to 7.5 or whatever this other endpoint is right here, but all the stuff in between, all the like 1.2, 1.3, 1.4, all of that gets included now. And Hopefully, most of you still have. I passed out all that stack of papers that had all the charts and everything on it, because those charts, we're going to use them here in a minute, because the charts show us this. And what the charts do, where if this was a histogram and the bar looked like this, the charts help us to get rid of those extra parts that are above the histogram. All right? And you probably, if you look at this, you could probably say, you know, if we were going to estimate this, you see that little part right there? Could we move it? Could we move it like right over to here and fill in some of that? And this little part we could move to here and fill in some of that, and so on and so on. And if I could draw a good curve, it really look good. But that's what the charts do. And your calculator will do some of it also. So it does all that, and it sort of estimates it to this normal curve. Not sure why I have that picture on it twice. What makes something a normal distribution? Normal distribution, continuous, it's going to look like a normal curve, the bell curve. For some random variable, whatever it is, our random variable normally we have is x. Doesn't really matter. Again, most of this right here is just explaining that, and hopefully you know most all this. We're dealing with some variable. It's going to be continuous. We're going to find the probability. And there's going to be certain things that work with this normal curve that you're going to have to know as we go through it. And most of them, a lot of them are common sense. If I take that right there, that's probably where our mean's at. What's the probability that I pick something that's in that side over there? 50%. What's the probability that I pick something that's higher than that mean? 50%. That's one of the properties of a normal distribution. What's the other name that we said it? So it's called a normal curve, but it could also be called a what? A bell curve, if I could write. Bell curve, I don't mind whichever one. Normal curve, bell curve, all the same thing. So we have a normal distribution. This is a paranormal distribution. One of the few jokes I have, Gage, so you better laugh now. Because
That one was pretty hilarious. You see what he did there, Bill?
I'm glad I was awake for that one, but I think it's time for a nap.
You're gonna put that grade, that test over zero? So that grade that I have already is,
I think I did.
my final grade, it says zero.
If it says zero, it doesn't say
It
dash.
says zero, I still got a 92, so I can do it. Do it, turn it in, and then Elijah needs to
Go up there on my desk, and one of the piles, I think it's laying right on the top of the middle pile, right there in the front. All right, properties of a normal distribution. These are some of the main properties. The mean, median, and mode are all the same. Mean, median, and mode are all the same on a normal distribution. So if you know the mean is 20, I guarantee, Sean, I put one of these questions on the next test. I'll say, the mean of this is 20. Find the mode. And everybody's going to go, what? We never learned that. What? And it's just going to be 20 because they got to be the same. So mean, median, mode all have to be equal for it to be normal. It's bell shaped, symmetric about the mean, so the mean's always right in the middle. The total area under the curve always equals 1. Usually it comes back up. It doesn't act like it's going to this time.
Get my lap. I got it back.
It's funny because there's still a light.
Is the light still on?
Got it back.
Yeah.
Great. Put it on. It's gonna do the same exact. I was gonna go straight.
Imagine there's just like a big stink bug on it. And we can't see it.
Those dogs, they don't play like that.
Or it's just a really big spider. It's nowhere near you. If it was a big spider, it'd get Brendan first.
So spiders can jump.
Some spiders. Yeah, most
Stingrays
spiders.
fly. Cockroaches fly. The dive bomb. They don't even fly. They dive bomb.
I'm sorry, Jake. I'm sorry. It's probably fun. I should ask you to go to the bathroom. Give me more time to get my next step. Ready for my naps. Sorry. She said she had to pee, so she should ask you to. I wasn't telling her what to do, I was suggesting. I was suggesting that she does that. Well,
It's coming back up.
good observations.
It's worrying me because it looks like it's coming up dark. Maybe something's not quite right.
You're not fresh.
Be a man.
Your mom's not.
So total area under the curve is always 1. Just like the probability, total probability of any situation has to be 1. The total area under that curve is 1. Hopefully in some of your other higher level math classes you learned this. The number 4 there. As you get down to the x-axis, you never ever really reach the x-axis. Probably in your other classes you call it an asymptote, where it's getting closer and closer to something, but it never really gets to it. That's what you're doing with the x-axis.
Is there fun calculator stuff for this? Is there calculator stuff for this?
Yeah. I think this is sort of, as far as the calculator goes, it seems like this is sort of pain in the butt. Because there's so many different ways you can do it. So, in the past, it seems like some students have decided to just use the charts. But
We did that with last time.
that'll be up to you. If something, because sometimes it's easier, sometimes it's not.
Gage, when do you guys play Checker Village?
I'm just getting tired of it.
Gage, when do you guys play Checker Village?
Tuesday. Not this Tuesday.
Is it at home?
It's home.
Yeah. I thought today was Monday.
Other properties. Now with this, I don't even know that I'd write this down. All right. First of all, inflection points. We're not going to deal with inflection points a whole lot. We talked about them earlier this year, and I said we don't deal with them. Inflection points is where it's that point where the curve stops increasing and starts decreasing, or vice versa, depending on which side of the curve you're on. We're not going to deal with that a whole lot because I don't want to go into all the math. That's more calc and stuff like that when you deal with that. With this, just know down here at the bottom, when we make these normal curves, and you're going to have to draw a bunch of these, even if you use your calculator for all the stuff, I'm going to put on there, draw it. All right? So you're going to have to draw these. The mean's always going to be right in the middle, whatever that number is. And then you go 3 standard deviations up, 3 standard deviations down. Does everybody remember that when we talked about that? So that's the way our curve's gonna look. What do we know about stuff that falls out here? It's an outlier, all right? Very unusual. What do we know about stuff that falls in this area?
It's like top 2%.
Right, it's unusual to happen. It's unusual for it to be out there. So unusual here, unusual out in here, very unusual to be outside of 3 standard deviations away from the mean. The one thing I will say, because I can't remember what all I have on my slideshow here, what you're going to have to draw, you're going to draw a normal curve, and I'm going to draw a lot of them. The mean's always going to be right in the middle. Whatever that mean is, it might be, let's say the mean is 100. And a standard deviation, remember that's the sigma, standard deviation, maybe it's 10. Just to make something easy. You got to be able to figure out the numbers. So that'd be, oops, not 90. That'd be 110, 120, 130. Going the other way would be 90, 80, and 70. Be able to draw that. This is using raw scores. If we want to do a standard normal curve, then our curve is going to look like this, and it's going to match up exactly to this, except the mean now is going to be 0, 1, 2, and 3. This is using the z-scores, and then -1, -2, and -3 going out the other way. So those are the 2 curves, and we're going to use them a bunch. They're probably on here, but just to make sure. The inflection points, again, I don't care about the inflection points. Remember, mu is mean. Hopefully you know that by now. Hopefully you know that sigma is standard deviation. And sorry for some of you, because I wrote sigma as standard deviation, and that's sort of wrong because I marked it wrong on your exam. What else should I have out here? Of a population. Sigma is the standard deviation of population. What's the other one for a sample? S. So make sure you remember those. Don't write any of this down. If we wanted to, Gage could take his calculator and he could type in that formula right there, and it would graph a normal curve for him. We don't want to do that because number one, the formula is sort of a silly formula. And number two, as soon as you start, when Mr. Alexander was here, he was good at this stuff. I'm terrible at it. When you start typing this stuff into your calculator to graph something, it screws up everything else on your calculator. You got to go back in and reset your domain and range and all the X's and Y's and everything. It messes all that up. So we won't be doing any of that. Normal curves, just a couple of things. Remember, pi is 3.14, e is 2.718. All that's on your calculator. The mean is the line of symmetry on the normal curve. And the sigma, the standard deviation, tells you how much it spreads. So just hopefully you remember those 2 things. We talked about them earlier this year. Sigma is how much spread you have. Mean is right in the middle. It's the line of symmetry. It splits the curve exactly in half. What if I have something like this? Means 20. Standard deviation is 0.5. And then I have another one. Mean is 20. Standard deviation is 5. So I'm going to explain how you're going to know the graph that goes with each one of these. What's going to be true about this graph in relationship to this graph. What's that standard deviation tell us again? spread. All right, so the first one, if it's got a standard deviation of 0.5, what's going to be true about that graph? It might look something more like that. That's still a normal curve. This one's got a standard deviation of 5. What's it going to look like? It'll be more spread out. So the bigger the standard deviation, the more it's spread out, even though the means were the same. So normal distribution can have any mean, any positive standard deviation. It's always got to be a positive, can't be a negative. Standard deviation wise. The mean gives the location of the line of symmetry. That tells you where the middle's at. Standard deviation describes the spread. Again, all these have those inflection points on there. I don't care about the inflection points. Probably should, but I'm not a good prop stats teacher, so we're not going to care about it. Somebody estimate for me, what's the mean of the first graph up there?
3.4.
3 what?
3.5.
3.5. Anybody guess how much standard deviation it is? How many standard deviations should there be from 3.5 out to about 7? Should be about 3 of them. So how could you estimate the standard deviation for that?
Like 1.1 to
1 point something? How about the second one? What's the mean of the second one? About 3.5. What's the standard deviation for that? Just an estimate. If you say 50, then yeah, that's wrong, but most likely I'm not saying. Say what? Maybe 0.5, somewhere around there.
2.
Next one, what's the, I got it. What's the mean of the second one? Or the last one, I'm sorry. 1.5. About 1.5,
Yeah.
and then standard deviation would be that 0.5 or so, whatever. So just, you got to be able to look at these graphs and know that these are still normal curves, even though they look different. Where the line of symmetry is, that's the mean. Got 3 standard deviations going that way, 3 standard deviations going that way. All basically the same setup. Which normal curve has the greater mean, A or B? Everybody agree with that? Now, is it because A is taller? No, it's because A comes out to here and the mean is going to be somewhere about in there, about 15. Which curve has the greater standard deviation? B. Right, because it's more spread out. Which curve has the highest mean? C. Which curve has the largest standard deviation? B. And it says find each line of symmetry. If they want you to do that, then you just come in here and draw your line of symmetry. Hopefully you can draw a little better than me. It'll be somewhere about there, and that's about where the mean for each one should be. Scale tests for New York State grade 8 mathematics test are normally distributed. The normal curve shown below represents this distribution. What is the test mean score? And estimate the standard deviation. Somebody estimate the mean for me. 675, everybody agree with that? Now, standard deviation is a little harder if I'm thinking 675, it might be a little more than that, I don't know. 675, somewhere about in there. How many mean, or how many standard deviations should we have on this side? 3. So if you're going from 675 to maybe 775, what is that? 775 minus 675, what's that? 100, and then we want to divide that by how many? 3, 33, 35, maybe, something like that, something close to that. That's probably a pretty good estimation. Wow. Again, I'm showing you this, do not write this down. This is how to graph it on your calculator, all that other stuff. We're not going to graph the normal curves. This would just, on your calculator, it would pull up and it would show you the normal curve. We don't want to do all that. We want to know how to find the probability of this area over here, and I'm going to show you how to do that, but we're not going to do the other stuff. We're not going to graph it. And it says try, we're skipping that. This is important. We did some of this on the exam. How to change from a raw score to a z-score. Raw score to a z-score. And what we're doing is we're changing from a normal distribution to a standard normal distribution. You throw that standard word in there, and all you're doing is changing everything to some score, where we can compare Ben's score to Alexa's score. Even though Ben's a male and Alexa's a female, we want to be able to compare them. And this is how we do it. And you should be able to draw either distribution. Again, I'm going to draw it again. This is where I should have drew it the first time. That's horrible. This is our mean. Maybe it's 100. And if our standard deviation is 10, then we go like 110, 120, 130 out to this side, and so on the other side. These are using raw scores. If we're changing it into the standard normal, then it's always going to be the mean is 0, 1, 2, 3 on this side, -1, -2, -3 on the other side. These are using z-scores. So you got your raw scores and you got your z-scores. On your calculators, when we do this stuff on the calculators, you're going to have to know, because it's a little different. For the raw scores and the z-scores, the calculator needs to know, hey, are you doing raw scores, you doing z-scores? So the way you type it in is just a little different. That's where when I was talking to Phoenix a little while ago, some students just like using the charts, and the charts, if you're using the charts, those are all z-scores. You got to change everything from the standard curve to the, from the normal curve to the standard normal curve. Make sure you remember this. Again, we had one problem on the exam that asks you to change from a raw score to a z-score. You're just using that formula. Your score minus the mean divided by the standard deviation. And some of the stuff that we plug into the calculator will actually change it for you. decide to do it that way. Got it memorized yet, Gage?
That? Oh, no. Yeah.
So when I make it, when I make it,
Is the Blazers wood?
yeah. Pretty special.
Huh?
Pretty special. I think I cut all those out,
The letters or the words?
the letters.
Cut out, why didn't you just cut out the words?
I mean, the letters for Blazers, I cut them out.
Oh, I thought you were talking about the individual. Okay.
The wood ones. You asked, you asked me about the wood ones.
Yeah,
so
but I
that-
thought you were talking about the
I
other ones.
literally didn't know what half the song was until like last year.
You score 25 on the ACT, and this affects some of you guys right now. You score 25 on the ACT, and you go take the SAT, and you score 1130 on it. Which of those scores should you send to the colleges that you're looking at?
This one keeps me.
The 25? Is that what everybody thinks?
I don't know anything about that.
All right, so what we do here, because we can't really compare ACT and SAT, right? So what we do here is we use that we just had and change them into Z-score. You probably don't, and you may not want to send them both, because maybe one of them's crappy, and they're looking at you and going, oh, wow, look, this SAT score. And then they go, what happened on this one? The ACT, they did terrible. Maybe they just got lucky up here, and they say, yeah, I don't know about that. So all you gotta do here is you take your score, which let's do the ACT first. 25 minus, and then down here it says the mean score is 20.8. How about a calculator so you can help me here? Standard deviation is 5. Figure out what that is. We're changing these all into a standard score. Then your score on the SAT was 1130. The mean score is 1060. And the standard deviation is 217. Now, once we get these both in that Z-score, in that standard normal score, now we can compare. Anybody get this top one yet?
0.84.
Does that make sense for it to be 0.84? Yeah, it means, what that's telling you is on your normal curve, on your standard normal curve, this is 0, this is 1, you're somewhere about in there, about the second one.
0.322.
So on your standard normal curve, now instead of being somewhere about in there, you might be somewhere about right in there. So which score is actually the better score? The ACT would actually be the better score to send to those schools. So standard normal distribution, again, this is what it looks like. I've said it like 10 times already today. So if you know that, remember that this area is always 1. The area that's underneath there is always 1. Again, what's the area from here down? 0.5. So on, so on, so on. We already did all that. Just got to transfer 'em from from the raw scores to the Z-score. Transfer them from raw scores to Z-scores. Remember, in these raw scores, it's just called a normal distribution. With the Z-scores, it's called a standard normal distribution. I'm repeating myself like over and over again here. That's the same thing as we did before, and I told you to just forget about it. See you guys later. Trying to get their grades up. Couple of things here, properties. Cumulative area is close to 0 for a z-score close to negative 3.49. So if we're down here somewhere, 3.49, what they're saying is from there over that way, what area should you have under the curve? Nothing, 0. All right? What area should you have going this way under the curve? 1. 100%, 1. What area should you have from here over? Nothing. What area should you have from that way going back? 100% or 1. Cumulative area increases as the z-score increases. On the chart and on your calculator, what they're going to always tell you, same as what we've done up till now, if we want to find, if that's your score right there, and we want to find something about your score, the chart or your calculator is always going to tell you the area below. Right? And that area is going to be the same as the probability. I've said this like 10 times. Area below 0 is 50% or 0.5. Same thing on that side. If we're looking at cumulative area from here down, it's always going to be close to 1 or close to 100%. Let's guess right here. What area do you think we have from there down, that shaded part? 75% maybe? Maybe a little more than that, I would guess, probably 80% somewhere. What area do you think you have from here down? 25. Say it again? 25% maybe? Maybe a little less than that. On your charts that I gave you, the very front 2 pages are those charts. So if you have those charts, front 2 pages are those charts, and we just match it up. You might want to get them out, and we might do something here in a second. No, you don't want to get them out, that's fine. So the bad thing about these charts, they only do z-scores. So if I gave you a z-score of 1.32, I look over here, I go down to 1.3, and I come over to 0.02, that's the area. So if I'm looking at my normal curve and I'm at a z-score, that's 1, that's 2, and 3's right here. I'm looking at z-score right here. They're telling us that from there down is about 0.9066, or about 91%, 90 to 91% of the data. So the probability of getting a score that's in this range is about 0.9066. Now for what they did 1.15, 1.1, come over to 5, be right here, 0.8749. That's the probability of getting that score or lower. Oops. Got to show my motion here, all this spectacular work that I did. So we're looking at that area right there. What if that's your score and you wanted to know how many people scored higher than you? Just subtract it from 1. All right? And that's what's going to mess up some of the stuff on the calculator, because the calculator doesn't understand that, and you're going to have to know, hey, I don't want this area this time. I want this area over here. So, and using the chart, you also have to know that. Negative 0.24, go down to that, go over to there, 0.45, so here down, 0.45 or 4052 is the area, the probability. Area probability, same thing. Calculator. Notice on this. To the left, I'll give you a second to write that down. When you're using your calculator and you want to find the area to the left, Michael, hold up your left hand. All right. Everybody see what? Phoenix, you might want to look at Michael. There you go. Make sure you know which one's your left. So if we're trying to find the area from that number, whatever score it is, down, then we can do this. If you have your calculators out, I'll go over it with you. We'll do one here in a second to just try to. Riley, we found bars on yours before, right? Notice it says second bars, normal CDF. And then the low limit, negative 10,000. It doesn't have to be that. That's just a number that if we're at negative 10,000 on our curve, and I'm going to do this a lot, there'll be a positive 10,000 also. If we're at negative 10,000 down here, what do we know about the area from there to the left? It's 0. So that's just a big number to get us way out here somewhere where we know we're getting everything, is all that does. So if Michael says, I don't want to put that extra 0 on there, it's probably not going to make any difference. All right? So if we get out to negative 100, we're probably far enough out also. All right? That's just giving us an arbitrary limit on this end over here that doesn't matter. Then you got to make sure you can find your comma. Then you're going to put in the z-score, close the parenthesis, and then hit enter. So if we put in, we know that if we're right here at the mean, if we're at 0, if that's our z-score at 0, what should the area be to the left? 0.5. So let's just type that in. Let's hit second, bars, normal CDF. Now mine says 2. Has anybody got something different for normal CDF, or is it the second one? Is it the second one on everybody's? Right, because they've been different all year. So you hit that, then in the parentheses, put in negative 10,000 or whatever you decide to put in, comma, and then our z-score this time is 0, close the parenthesis, hit equals, and what's it tell you? 0.5 with a bunch of zeros, and it's got another 5 out there at the end. Don't worry about that other 5 because we're on one out like 4, 5, 6 spaces at the very most. Yours different. So you got, so some of you may have this, a gauges calculator there. This is your lower limit. And your z-score this time is your upper limit. And what else does it ask you?
The mean and standard deviation.
And it asks you the mean and standard deviation. Well, the mean this time, since we're using z-scores, the mean is 0 and the standard deviation is 1. So you don't even change those. And you just go down to paste and hit paste, and
What was the z-score?
0. We're just using 0 now just to check it out. Now the good thing about Gage's calculator is it has them listed. He doesn't have to worry about what we're getting ready to talk about as far as, right now we're using z-scores. And then we could be using raw scores. So he's just gonna change that 0, the mean, to whatever the mean was in the raw scores, and the standard deviation to whatever it is. And it just listed out there. So Texas Instrument got smart when they did it that way instead of, for some of the older calculators, it does it a different way. On these, something that I want you to do every single time, sketch the curve. Even on the test, sorry Riley, but you're going to. Sketch the curve. All right? Doesn't have to be anything spectacular, doesn't have to be pretty. And then once you sketch the curve, I want you to put in the score that you're looking for. Maybe you're looking at this score right here. Mean, always put the mean in there, whatever it is. And you're looking at this score. And then I want you to decide, which way are we looking at? Are we looking at stuff below that or above that? So if we're looking this way, then you're going to shade in that area. If we're looking the other way, then you're shading in the other side. I want you to sketch it so that you don't mess up and tell me the wrong answer just because that's what your calculator told you. All right? So always sketch the curve, draw in the number that you're looking at, wherever it's at in relationship to the mean, how many standard deviations, whatever it's out, one way or the other. And then we can use the table. Probably not going to use table, you're probably going to use your calculator. Now, Maddie told us a second ago, what's going to be different if we're not looking at the stuff out to the left, if we're looking at the stuff out to the right? What would we do differently? Could we find this area first, just like we just did, and then do what? Subtract it from 1. That's what you're doing. Now, your calculator is going to do that for us, especially like when I looked at gauges. All he's going to do is now this score right here, instead of being the the upper limit, the score is going to be the what? Lower limit, and we're going to put in something like 10,000 going out this way because we want the calculator to calculate everything out this way, and then the calculator will know to subtract from 1. So, and that's why I was just talking about, if we're going the other way, then we just have to find that area, subtract from 1. The calculator is going to do it. This is how you do it on your calculator if you're looking for the area to the right. So you're going to have a lower limit, a higher limit, and you just put it in there, and then hit all the stuff. And all of this, both these, you might, for these last 2 things that we've written down, these will only work if we're dealing with z-scores. So if you're dealing with raw scores, it's something a little different. Again, for my higher limit, I put in positive 10,000. If you go out to 100, that's probably far enough, 1,000, whatever. I think I was just punching zeros and so stopped at 10,000 and as we do all this, don't forget what you're finding every single time. You're finding, we're here and we're looking for this, we're finding that area, and that area is also the probability of getting a score that's from this number and up. So area and probability, they both mean the same thing. So what do you think we'd do if we were looking for this area in the middle? Instead of going clear out here to 10,000, now what's our upper limit? 1.23, what's our lower limit? So we just type those into our calculator, and it's gonna tell us that area that's in the middle of them. This is for if we're in between. The only thing that changes on this, instead of having the negative 10,000 or a positive 10,000, you put in your lower limit, and you put in your upper limit, and you put a comma in between. So nothing hard about it. It's just, yeah, I want to go from -1 to +2. Then you put in the lower limit, which is -1, the upper limit that's +2. You figure it out already.
Yeah. It's pretty easy.
Now, again, the bad thing with all these, all of them deal with z-scores so far. Everything's a z-score. I'm not gonna do all these because I want to get to the last thing here. You heard her stop. Didn't she just tell you to stop?
And she said sorry.
No, I said that was loud.
Oh.
So you didn't hear her either. Now, we could do it all this way and do all this math. Sort of pain in the butt. I honestly keep wanting to jump back on me. Good thing we have the calculators. We already wrote that one. Remember your z-scores? You got your mean, I put X bar on this one, same thing. Very unusual is out here, unusual. Very unusual, unusual. Hopefully you remember those two. Does everybody remember the empirical rule where it had the 34%, 13.5, 2.35, and so on and so on? So we're going to skip over that real quick. Didn't have it on here. Thought it did. Let's do this. Calculator. I wanted to try something here real quick. So 0 to 1 should be about 34% if we're doing standard deviations, right? So let's try to make up one so we can write down the stuff on the calculator and make sure I'm right. If we go, let's make our mean 100 and our standard deviation 10. So on our calculators, and I'll write down the process here. I think what we do on the calculators, I thought I had this on here, but apparently not. This is for raw scores. Instead of have to change everything into a z-score. For raw scores, we hit second, bars, go down to normal CDF, think. Hit enter. And if we're just doing raw scores, instead of changing our 0 and our 1 into z-scores for this, which wouldn't be hard for this one, I'm pretty sure all we do is we put in our upper limit, or no, sorry, we put in our lower limit, then we put in our upper limit, then we put in the mean, and then we put in the standard deviation with a comma in between each one of them. And then you close the parenthesis. So let's try it with this. So if I go second bars, normal CDF, and I put in our lower limit this time, we're going to go with 0, comma, our upper limit is 1, comma, our mean is 100, comma, and our standard deviation is 10. And then close the parenthesis. So we went from 0 on our curve, we went from the mean to 1 standard deviation above, so we're just looking for that part right there. We hit equals, it should be, see, that says 0, so I'm typing in something wrong. What am I typing in?
What did you say the higher?
1. Oh, I typed it wrong, that's why. Anybody else get something different? Second bars, I typed all mine. So lower limit's 0, upper limit's 1. Trying to do this to make it easier on you, because I think this first assignment, you're not supposed to do all this, you're supposed to change everything to Z-scores. Just hoping I can make it easier. Our mean is 100. Our standard deviation is 10. When you're typing in on yours,
Still be 0.
I got 0
I got a very, very small.
and you put in your mean is 100 and standard deviation is 10.
Negative 23.
So from 0, why would we get
22
2?
zeros in front of that.
Because from here to here, it can't be 0. Oh, yeah, it could be. Stupid. We're not changing it to Z-scores. Dumb. Dumb. So our lower limit. What's our lower limit this time? 100. Idiot. So we hit second bars, go down to normal CDF. Our lower limit's 100, comma. What's our upper limit if we're going up to 1 standard deviation above? You add 1 standard deviation, right? So 110,
So,
comma.
oh,
And what's our mean? 100, and what's our standard deviation? And we get, is it pretty close to 34%? I'm just telling you, I go to call you, so you're busy looking at your phone. After I told you not to.
I got last place in my hands here.
Good.
I'm scared.
really messed
That's
up.
what you get for messing with your phone while you're in my class.
My sound working.
What's the home?
Why would you say
Oh, my fault.
Why would you say it? Nice, thanks, Joe.
I already sent it out on the email, so.
Oh, okay. Well, that sucks.
Work together.
That's the assignment.